Bismillahirrahmanirrahim. We'll solve problem 386. This is a rigid tank. We have a tank fitted with an artificial resistor of negligible mass. Holds 1 kg of nitrogen. So we have the mass equals 1 kilogram. We have the nitrogen as our system. T1 equals 27 degrees Celsius. So let us just immediately convert it into Kelvin, because that's what we need to use generally. So this is 300 Kelvin. P1 equals 0.2 megapascal. The resistor at a rate of of a period of 5 minutes, electricity provided to the resistor at a rate of 0.15 kilowatt. So this is the rate of the electrical power work. So this is W dot, because it is power 0.15 kilowatt, and this will last of delta T equal 5 minutes. Okay. Assuming ideal gas behavior, determine the nitrogen final temperature T2 in degrees Celsius and P2 in megapascal. Okay. All right. So for nitrogen and for any ideal gas, we either use constant specific heat or the tables. So let's solve with both methods. So we have the energy equation Q minus W equals delta U, and the kinetic and the potential energy change are negligible. So this will equal M U2 minus U1. Okay. Or we can write it as M CV T2 minus T1. Okay, so let's solve it first, assuming constant specific heat, and we use this relation of delta U, CV times delta T. So Q, we are given Q here. Okay, this is معنى Q هنا لا ماشي. Yes, there is heat transfer of magnitude 12. So we have Q equals 12.25 kilojoule. But we should be careful here, read the question carefully. We said it says that the heat transfer occurs from the nitrogen to the surrounding. So this is heat transfer to the outside. Therefore, Q is negative, because that's the convention. If the system loses heat, then the heat is taken as negative here. So what we have here, minus 12.25 kilojoule minus the work. We don't have boundary work, but we have electrical work, and that equals 0.15 kilowatt. So we need to multiply it by delta T. So here the work equals the power times delta T. We have delta T is 5 minutes, so we need to convert it into seconds. That is 5 times 60. So this will equal, the mass is 1. CV, we go to table A20, and CV for the nitrogen, okay, at 300 is 0.743 kilojoule per kilogram Kelvin. you should be really very careful when using the table. First, use the table of the gas that you are looking for. Here we are dealing with the nitrogen, and then you need, or we need CV, not CP. So we use this value 0.743. So here we have times 0.743 times T2, which we don't know, minus 300. And and here, okay, there is something that this is work input, and work input is actually negative, okay, because work in is negative according to the convention. So here we have negative sign, and this is negative work because it's work into the system. So this will become positive. Okay, negative and negative is positive. And if you solve this, you'll find that T2 equals about 344 Kelvin. Okay, or because here the question says find T2 in degrees Celsius, so 344 minus 273 is about 71 degrees Celsius. So we found the temperature. And of course here you notice that when we provide heater, the electrical heater, okay, it adds heat to the nitrogen. So it's only logical that the temperature will increase, will raise. Okay, so the answer is logical. Now to find the pressure, we go back to the ideal gas law. Okay, and again here, this is a rigid body, rigid tank, the tank volume is fixed, therefore V2 equals V1, therefore R T1 over P1 equals R T2 over P2, R cancels with R, and we have the famous relation between T and P. I am doing this so that I showed you that you really don't need to remember these special cases. So what we have here, P2 equals T2 over T1 times P1, and this should give you something like 0.229 megapascal. Okay, so we solve this using constant specific heat. We also can solve it using the tables. Okay, so but for the nitrogen, the properties for the nitrogen in this table is given in table A, in this book is given in table A23, and here it's in kilojoule per kilomole. Okay, but that's okay. So what we have this relation. Okay, so we have Q minus W equals M U2 minus U1. So again, this is minus 12.25, and this is minus, then minus 0.15 times 5 times 60 equals 1 times U2 minus U1, and U1 is a 300, so this is 300. So we go to the nitrogen, and this is the value. Okay, this is U, not U, this is the internal energy, okay, per kilomole, kilojoule per kilomole. So we have U1 equals 6229 kilojoule per kilomole. So we divide by the molar mass of the nitrogen, which is 28.01. This you can get it from table A1. Okay, and so this is 222.38 kilojoule per kilogram. So this is your 222.38 kilojoule per kilogram. From here, we get U2, and if we solve for here, okay, it's very simple. Just see here negative and negative, so this will be positive, and what we will have here that U2 equals 255.13 kilojoule per kilogram. So now we have this value converted into, so multiply this by again 28.01, and this will give you 7146, okay, kilojoule per kilo mole. Now we look for this value in the table for the nitrogen, so 7146, so it's between this value and that value. So our temperature is between these two temperatures, 340 and 350. So what you can do is to do interpolation to find T2. So from this, do the interpolation and find T2. But you notice here that the temperature is between 340 and 350. And our temperature, which we found it using constant specific heat, is also between this. It's 344. So our temperature using constant specific heat is close to the temperature that we will get using the tables with the variable specific heat. And then after that, of course, you will find the pressure. So that's how to deal with this, with the tables. Of course, for air, it is simpler because the tables of air are already in kilojoule per kilogram. So you can get the values of the internal energy easily from there with the units that you want. Okay, thank you.